All right, so let's see if we're live again. Give it a moment to check the audio. I think I got everything. I updated the other videos, started a new stream, all the different tasks. Kind of doing it quickly now. Started a new stream, all the different. Yeah, okay. Audio is fine. Pop out this chat now, and we can keep going. So this one is going to be minimum number of domino rotations for equal row. And I think I got everything. Hold on a second. Yes, pretty sure should be fine. All right. Let's do that. It's like a bunch of things I'm doing at once, so yeah, we'll just go right into the next one. Just keep going. So minimum domino rotations for equal row. In a row of dominoes, tops 1 and bottoms 1, or tops of I, bottoms of I, represent the top and bottom halves of the ith domino. A domino is a tile with two numbers from 1 to 6, one on each half of the tile. Okay, so the dominoes have two numbers, right? Top and bottom numbers. Okay, that's a good picture. I like this picture. We may rotate the ith domino so that tops of I and bottoms of I swap values. Return the minimum number of rotations so that all the values and tops are the same, or all the values and bottoms are the same. If it cannot be done, return -1. So may rotate, say swap, minimum number of rotations so that all the values are the same, or all the values and the bottoms are the same. If it cannot be done, return -1. Oh, that's interesting. So tops, bottoms. Oh, interesting. Okay. To get all the tops to be the same, you would rotate these two. Okay, well, I guess you've got to pick a number for the top and the bottom to make the top all the same, or to make the bottom all the same. That's interesting. Huh. I think this is actually not that hard. I think it's just like a frequency map kind of a calculation. Numbers are between 1 and 6. Okay, yeah, this is like linear. I think you do it in linear time, because the frequency map can be just very straightforward. So let's do top frequency and bottom frequency and think of it in terms of that. So basically, if the top frequency of values and the bottom frequency of values, if you add them together. Now, you got to be kind of careful, though. It's got to be unique frequencies. The total unique frequencies for a particular position needs to be greater than or equal to n for it to be possible for a particular value, right? And then on top of it, not only does the unique frequency for each particular index need to be greater than or equal to n, but also you need to take the smallest one. So there is a certain number of, for each frequency, there's a certain number of these values that are at the top and a certain number of them that are at the bottom. And basically you take the difference between these numbers, right? So whichever number is smaller, whichever number is larger is what you want to take, and you want to do n minus that. So here you have 1, 2, 3, 4, and n is 6. So n minus 4 is 2. You'd want to take the 2 at the bottom and shift them up. That's what you want to do. Yes, so you take the maximum, n minus the maximum of those values, of the ones that are equal to n. So you could do it like the following. You do a top frequency and a bottom frequency. Top frequency of 6, so we're going to just say bound. Bound is 6. Bottom frequency is BD. Fill both of those with zeros. Top frequency, just TFQ, BFQ. Yeah. Oh my goodness. Top frequency, bottom frequencies, fill those with zeros, loop through both auto x and tops, or it's actually int. These are actually 1 through 7. Okay, so we're just going to add 1. Top frequency of x, increment by 1. Same thing here. And bottom frequency. And whoop. Oh, no. And then there's the unique frequency, which is a little bit different. Now we're going to say the top frequency, bottom frequency, and then unique frequency. Oh yeah, I didn't really explain this part. The unique frequency is going to be if, it's going to be like this. Unique frequency. It would be whatever this value is at the top and the bottom. It's going to be like the following: unique frequency of tops of I. And then we would say if bottoms of I is not equal to tops of I, then also take the unique frequency of bottoms of I. Yeah, so that's kind of subtle. That's kind of subtle. The issue there is, and actually you don't really need to do these either. You could just do A is tops of I, B is bottoms of I. You could do A. A is not equal to B. And then increment top frequency of A and bottom frequency of B. Technically one pass. Now we're going to say if the frequency, and you could do this same thing here, result, come back to that in a moment, what the result is supposed to be. If the unique frequency of A is equal to N, or unique frequency of B is equal to N, which actually, yeah, I'll just do it this way. Actually, that's probably not 0, or I is 1 really, I is less than BD. It's probably easier to do it this way. So if the unique frequency of I is greater than or equal to N, then we're going to update the result to be, it's N, the minimum of N minus the maximum minimum of itself, and N minus the maximum of the top frequency of I and the bottom frequency of I. Yeah. Okay, I realize that's a little confusing what's going on there, but it's more or less what we're after. And this should have been pretty quick. 9 minutes? Yeah, it shouldn't have been. N is oh, let's do it this way. Tops. Yeah, okay. Which case this is just N. I think this is it. Something like this. So there's unique frequencies, there's top frequencies and bottom frequencies, and this result should always be, should start off at -1. Oh yeah, let's do N plus 1, and this is going to be result equals N plus 1. Then we return -1, otherwise return result. Something like this. Sorry about that. If it's not possible, I have to handle that correctly. Yeah. That's sort of a sentinel value. I could use an optional for this too, but I don't really have to do that. Yeah, so it works in those two test cases. So again, the idea is I'm going to use a frequency map for each number, and I'm going to have 3 different frequencies I keep track of. The first is the number of times I see something at the top. The second is the number of times I see something at the bottom. And the unique frequency is how many elements I see between the two of them for a particular number. Meaning at each index, there could be 1 or 2 different numbers present. And I'm only interested in the particular values that have enough unique frequency to be able to be moved all the way into one direction or the other. And then of those possibilities, right, for each one, there are 2 options again, where I could either flip all the dominoes down or flip them all up, right? And I'd want to take, of those 2 options, I want to do the fewest number of flips, which means that I want whichever side has the largest number present, that's the side I want to pick to flip things into. And the number of flips required then once I pick that side is going to be n minus whatever that number is. So I could take the maximum of those 2, take n minus that, and then that result I want to minimize over all of the possible selections. So it's not too hard, not too complicated, but it's definitely kind of involved. Not too easy to explain, I suppose. Let's see, let's do 5 as something I can flip everything to. Okay. I'm going to submit this because it's going to take me a while to go through all the test cases. I think this is correct. I could be wrong, but I think it's okay. I think it's right. Yeah, let's try it. Could be wrong. I didn't really test it. Oh, there you go. Got it. Okay, very good. So yeah, let's submit this 4 more times, and then obviously I also have to properly handle the that sort of edge case when it's not possible. 1, 2, let's say 3. Let's do 5 times, and then I'll start the next question. The next question is, this is reasonable. This is a relatively fast way of doing it. Use a little more memory, apparently. So not a lot of memory. I don't know why it's 1100. I mean, this is not that much memory that's being used. I don't know. Weird that this is kind of slow and uses a lot of memory. I don't know what to say about that, but yeah. So I don't know. 100 megabytes is like, why is it using 100 megabytes? It's like 3 small arrays, but whatever. Yeah, 1, 2, 3, 4. We'll submit it one more time. I don't know why it's so slow, but whatever. This is what it is. So yeah, 1, 2, 3, 4, 5, and I think it's just a lot of test cases. It must be. We'll go to the next question. So construct binary search tree with reorder traversal. Can't make this larger. I'd like to. So yeah, I'm gonna stop there for this question. So if you like the stream, don't forget to like it and follow the channel. And I'll be back. I'm gonna restart the stream with a new title. So.